All right. Good afternoon, good day, everybody who is watching us this hour. So we are back again at it. We are transitioning today from what we have been looking at. Now, if you remember clearly, you will remember that last time we met, we did look at how to formulate linear programming problems and also how to graph the linear programming problems. And we're looking at a question last time that we the PC Tech question, if you can remember correctly. Yeah, so we looked at the PC Tech question that we did the first part of the question, which was formulating PC Tech's production plan. And just in case you forgot what we came up with, I am going to rewrite the objective function and also the constraints, so that we can be on the same page as we go through our question today, which will be looking at the simplex problem. Now, before I write what we did or what we covered last time, I'm going to introduce a simplex method. Okay, I'm going to introduce a simplex method and also tell us when to use it, and also some of the prerequisites before we can even dare to use the simplex method. Now, as I have already mentioned, once you have a linear programming problem formulated, most questions that you're going to encounter in the exam or in the test, if it comes, will most likely, the next issue or the next thing which will be required to do in that question is to solve it for what are called your optimal values of the decision variables. Okay, now those optimal values that you're going to solve for will lead to either minimization, which may be, for example, costs, or it may lead to maximization, which may be, for example, profit. Yeah. Now, the graphic method is very much available to handle solving for optimal values. As we know, we have already covered the graphical method. However, it has its own limitations. Okay, for example, when only 2 items are produced by firm, or if you're an investment manager, for example, if you're managing a portfolio on behalf of your clients, you may have maybe if only 2 investment opportunities are available to an investor, you can use the graphical method. Or if you are an advertising agency and you are deciding which 2 advertising medias are available to you. Okay, in other words, what we are trying to say is, if you have only 2 decision variables involved, then we can think about a graphic solution to your linear programming problem. All right, now, to be fair, in many cases, as a company or as an organization, you are faced with more than 2 decisions. Okay, or you have more than 2 variables that you may be considering. If you are an advertising manager, you may be considering whether to put or to place your ads in a newspaper, or on WhatsApp, or especially Facebook, which has an ad, or Google Ads, or LinkedIn, or Twitter, or any other platform, okay, or on TV or radio. Now, those are more than 2 variables. Now, in such, managers tend to what we call the simplex method, which is a very powerful tool actually for solving linear programming problems. Now, one thing that you must know is that the simplex method and its variants, the big M method, the dual method, those ones can handle any complexity in the linear programming problem, irrespective of the number and the nature of your decision variables or constraints. So that is what you have to know. All right. Now, when looking at the simplex method, or you may call it the simplex algorithm, one thing that you must understand also from the onset is that it is an iterative procedure. Okay, it is an iterative procedure for finding in a very systematic manner the optimal solution, as we have already said, to a linear programming problem. Okay, so that is the first thing that you must understand about the simplex method. Now, there are conditions. Okay, there are conditions which I'm going to write here, not all, just briefly. I'm going to summarize them. So there are what we call conditions. Okay, so let's see. So there are what we call conditions for application of simplex method. All right, so now here's the thing. In order that the simplex method may be applied to a linear programming problem, an LPP, there are two conditions that you must satisfy, or there are two conditions that must be satisfied. Okay, there are how many? There are two conditions that must be satisfied, and the first condition is that, please take note of this, this is very important. The first condition that must be satisfied is that the right hand side, or we can just say the RHS, because this is going to come back, the right hand side of the constraints. Let me even write the constraints. I'll change the color for constraints, and then I'll bold it, because this is important. The right hand side of the constraints. Yeah, so we're saying that the first condition is that the RHS, the right hand side of the constraints, should be non-negative. Should be non-negative. Now, if you have an LPP, or a linear programming problem, which has a constraint for which a negative resource value is given, the first thing that you must do, or the first step, is that you have to convert it into a positive value by multiplying both sides of the constraint by -1. For example, let's say we have been given a question, and this question is, for example, let's say it's 7. I'll just pick random values. It's we're going to pick 7. Sorry about this. Let me erase this. So let's say you have, let's even change the color. Yeah, so let's pick green perhaps. So let's say 7x1 minus let's say 2x2 is greater than or equal to -6. Now, if this is the case, what do? We need to multiply both sides by -3, or sorry, by -1. So it would be, you do your brackets, and then you multiply everything by -1, so that it will become -7x1 plus 2x2, and then when you multiply -1 by -6, you must make sure that you change this sign here. It will no longer be greater than or equal to. Instead, now it will be less than or equal to 6, positive 6. Please take note of the change in the direction of our inequality. So this is the first condition that must be met. Okay, now what is the second condition that you must meet? So the second condition that you must meet, or number 2, is that each of the decision variables of the problem should be non-negative. Okay, it should be non-negative. Now here's the thing, please take note once again. Sometimes a problem may have a variable which is unrestricted in sign, or we call it a free variable. Now what does it mean? It means that for such a variable, it can assume negative values, okay, as well as non-negative values. Now if you have an unrestricted variable, you can't solve for linear, you can't find the optimal solution to such a problem. So the first thing that you must do is you are going to treat an unrestricted variable as a difference of two variables, and those two variables must both be non-negative, or they should be greater than or equal to 0. Why are we treating such variables to be non-negative? Because such a difference may be either, it can be positive, or it can be negative, or even a 0. Let's take for an example here. Let's say you have been given in a question or an exam or a test. They have told you to maximize or to find the optimal solution to the following linear programming problem. So maximize z, or z max, is equal to 5x1 plus 6x2 minus 2x3, subject to the constraints. Now subject to what? Let's say x1 plus 4x2 plus 2x2 is less than or equal to 70. Then here you can be given 5x1 plus 3x2 minus 2x2 x3, sorry, so this is 3, is less than or equal to 40. The last one we can say x2 plus 5x3 is less than or equal to 40 again. And then now here is where you will know that you have been given an unrestricted sign when they tell you that x1 comma x2 is greater than or equal to 0 comma x3. They will tell you that it's unrestricted in sign, which means it's a free variable. It can take on both non-negative values and it can take on negative values. Now in such a case, what do you do? Okay, now listen, and listen carefully. Since x3 is unrestricted in sign, we are going to represent it by a difference of two non-negative variables. Now those variables can be anything. If you want, you can say x10 or x and x11, or x12 or x100 and x15,000, whatever they are. But as long as you can, they are logical and they are close to what we have already here. So in our case, let's say we are going to take two variables which are non-negative. We can say we're going to take x4 and x5. Now these two variables, or this x4 and x5, will be substituted for x3, such that x3, wherever there's x3, we're going to say x4 minus x5. Okay, and then we're going to simplify this. Now, how is our new linear programming problem going to look like? So here is how we are going to write it. Now we are going to say maximize z is equal to 5x1 plus 6x2, right, minus, open bracket, just open the brackets here, and then put where the z, where there was x3, what are we going to put? We're going to put 2, so it will be minus 2x4 plus, or minus, sorry, minus 2x5, and then we can simplify this further so that we have our z max equal to 5x1 plus 6x2 minus 2x4 plus 2x5. So this will be our new objective function. Alright, now once we have our new objective function, we can now go ahead and do our constraints. So this will be subject to what? Subject to x1, so this will be x1 plus 4x2, and then we can say plus, now we can either open brackets here and then do that, or we can just do it straight now here, since you've known what we are doing. Now we are going to get this value, the 2, and say 2x4 minus this minus here, and 2x5 minus 2x5 is less than or equal to, what was our value? 70. Less than or equal to 70. We go to the second constraint, which is 5x1 plus 3x2 minus 2x4, and then plus 2x5 is less than or equal to 40. Okay, 40. And then the last one, x2 plus, what is the number here? 5. So it will be 5x4 minus 5x5 is less than or equal to 40. Now once we have written this, the last thing now is we are going to say x1 comma x2 comma x4 comma x5 are all greater than or equal to 0. Now you've seen what we have done. We have removed the unrestricted sign, so our sign can take only non-negative variables now. So this was an example in case you have been given a question and one of the variables in that question is restricted in sign. So that is the first thing that you must do. All right, good. Now, having done this, how do you now find the solution to your simplex problem? That is the next thing that you're going to do. So we are going to say solution to maximization problems. Okay, now one thing that you must know, that all simplex problems must be of maximization in nature. That is one thing that you must be able to understand and do. That all simplex problems must be of maximization or in nature. It will even help you solve for the simplex method easily. Okay, yeah. Now, let's say you have been given an example. Okay, let's say they have told you before we can solve for our simplex method or for our previous problem objective function. Let's say I've been told to maximize, as an example, maximize z or z is equal to 40x1 plus 35x2 subject to 2x1 plus 3x2 is less than or equal to 60. So this can be, for example, raw material constraints. Then the second one can be 4x1 plus 3x2 is less than or equal to 96, for example. So this can be labor hours. Now, have you seen the way this problem has been formulated? You can solve this using graphical method, okay, because we only have two variables, decision variables, x1 and x2. So it's easier for you to solve this question using the graphical method. You can even try it if you want, and then also compare it with the simplex method. So solve it as a graphical method, or using the graphical method, find the optimal solution using the graphical method, and also use the simplex algorithm to find the optimal solution. So the last thing we do is we're going to say x1 comma x2 must be greater than or equal to 0, because you can't have physical negative values for physical quantities. You can't say we have negative 25 solar panels or negative 2 geysers or negative 5 tanks. You can't say that. So you can only have physical quantities or no quantities at all. It's 0 or it's either they're there or they're not. So this is our non-negative restriction. Okay, this is our non-negative restriction. Now I want to give you an example, okay, of using this, of some terminologies that you may be aware of: slack variable, surplus variable, artificial variable. But for this one, we're only going to look at the slack variables. Artificial and surplus come in later problems when we're dealing with the big M method and the dual method for the LPPs. Now, you see, colleagues, the first step, okay, take note of this statement, it's very important. The first step in applying the simplex method is that you must standardize the problem always. If you forget anything else, make sure you standardize the problem. Maybe you can get a mark on that one, because it's the simplest thing that you're going to do for a linear programming problem in terms of the simplex method. So we are going to say standardization of the problem as a step 1. Now, how do you standardize the problem? Now, for the constraints that we have, the first thing that we must do is we must convert them into equations. Okay, we convert them into equations. Now, for you to convert an inequality, or for you to convert our constraints into equations, you must add what we call a slack variable, or an SI variable, like this, an SI. Now this I can stand for any variable, or it can stand for any value. It can be 1, it can be 2, it can be 3, 10, 11, depending on the number of variables you have, decision variables you have in the question. Okay, now for the first inequality in our system, which is 2x2. Okay, so the first inequality is 2x2 plus 3x2 is less than or equal to 60. Less than or equal to 60. Now you see, this is our first constraint. Okay, it is the number 1 constraint in the system. So to convert it into an equation, since it is a first constraint, what we are going to do is we are going to add a variable s1 on the left hand side, so that now we are going to get 2x1 plus 3x2, and then we are going to say plus s1, and then is equal to 60 or 60. Okay, this is the first thing you're going to do. Now, if you solve for the optimal solution and you have found the values of x1 and x2, for example, okay, if 2x1 plus 3x2 is exactly equal to 60, then we are saying that the value of s1 is equal to 0. Okay, have you understood what we have said? Let me give an example. If, for example, this is 2 times let's pick a value. Let's say this is 2 times 15. Yes, let's say it's 2 times 15 on x1, and then plus this is, for example, 3 by 10. Yeah, 3 by 10 is equal to 60. So what is here? So this is 30 plus 30 is equal to 60. So this is 60 is equal to 60. Now you see the way this thing is here, because this side is equal to 60 even without the s1, then the value of s1 will be 0, because if you add the 0 here for s1, it will not affect these values here. Okay, now if you realize, or if you discover that 2x1 plus 3x2 is less than 60, then what we are saying is s1, okay, your slack variable, the s1 is going to equal the difference between the left hand side and the right hand side. Simply put, if you discovered that, for example, this was 5, okay, so that now we have 30 here plus, what is 3 by 5? 15 by 15 is equal to 60. So this is what? 45, right? So 45. Now we know that 45 is not equal to 50. In fact, 45 is less than 60. So what we are basically saying now is here is where we say 45 plus S1 is equal to 60. This S1 is going to take on the difference between 45 and 60. In our case, it will be 15. So S1 here will be equal to 15. Okay, I hope we are clear. Yeah. Now, this S1 that we have in our equation here can take on any values from 0 to 60 in our first inequality. Okay, in our first equation, sorry, here, our S1, this S1, can take on any values from 0 all the way to 60. Okay, all the way to 60. For example, if x1 is 0 and x2 is 0, then s1 will take on a 60, so that the left hand side and the right hand side should balance. Yeah, so the way we write that is 0 is less than or equal to s1, which is less than or equal to 60. This is how we write it. We basically mean s1 can take on any values between 0 to 60. Okay, between 0 and 60, any values there. Yeah, so as we have already mentioned, the variable s1 is called, or it is referred to as a slack variable. Why? Because it takes up any slack between the left hand side and the right hand side of the inequality, once it has been converted into an equation. So that's the example that I wanted us to have or to know as the first thing. Okay, it is the SC variables or the slack variables. Now, how do you actually standardize your linear programming problem? It's very simple how you standardize it. Okay, it's very simple how we standardize it. We have already mentioned that we convert these equations to these inequalities in the constraints to equations. Okay, so the first inequality, we have already converted it. It will be 2x1 plus 3x2 plus 3x2 plus s1. The s1 should be down there, should be a subscript. So this s1 is a subscript. The 1 is a subscript. So it's a 1 like that. Is should be equal to 60. What is the second one? The second one we had was 4. So we have a 4x1 plus 3x1 plus s2 is equal to 60. 96, sorry, is equal to 96. Is equal to 96, and then we have x1 comma x2 comma s1 comma s2 is greater than or equal to 0, like that. Now this is how you standardize the problem. Now one thing that you must know is this, okay? One thing that you must know is, you see this is a first inequality and it has an S1. This is a second inequality and it has an S2. The way we are going to write it when writing our standard forms, however, is we're going to do this, especially for the second one and the third one, if you have more than two constraints, is we are going to say 2x1, the way it is here, get it, plus 3x2 plus s1 is equal to 60. The second one, now we're going to say 4x1 plus 3x2. Now you notice that here we have no s1, okay? We have no s1. So what we are going to do basically is we are going to say 0 s1 plus s2 is equal to 96, and then bring your constraints down here. So this is the first thing that you must do. Now once we have done this, we also need to modify the objective function, okay? Why? Because the objective function for the simplex method should contain every variable in the system, okay, including but not limited to the slack variable. Now the reason I'm saying including but not limited to the slack variable is because when we start talking about the big M method and the dual method, we introduce artificial variables there, and we introduce surplus variables also in our objective function, which we don't do here. Now we shall have to add the s1, this s1 here, and the s2 here to our objective function, okay? Now before, please take note, before you add the s1 and s2 to the objective function, you must ensure that the coefficients of the s1 and s2 as they enter the objective function have been determined already. Now these coefficients we are talking about here may represent, for example, the costs which are involved when you don't use the raw materials or the labor hours in our case here. Yeah. Now what is important, or the beauty about the simplex method, is we basically presume, okay, that the unused resources have no cost at all, and because they have no cost at all, they do not affect the profits. Therefore, when we write our coefficients, they are assigned the values of 0, or they will be assigned zeros, so that, or such that, now our standardized objective function will be maximize z is equal to 40x1 plus 35 plus 35x2 plus, just say plus 0 s1 plus 0 s2. Okay, now one thing I am going to mention here is to make your life very easy when solving for the simplex method. I am going to advise you that make sure the z, the right hand side this side comes to the left hand side. What do I mean by that? So here is what I mean. To make your life easy, make sure this becomes z minus 40 x1 minus 35x2 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 then minus, so this can be minus plus minus s. In fact, this must be minus, sorry, yeah, so this must be negative like this, minus 0s1 then minus 0s2, so such that when they come here it will be plus s1 and then plus 0s2. So this is the standard form, okay, and then subject to 2x1 plus 3x2 plus s1, the one we already know, plus 0s2 is equal to 60. Then when we come to the second one, before x1 plus 3x2 plus, there's no s1 here, so it says 0s1 plus, now here we have an s1 s2, so it's 0s2. This is the second constraint, is equal to 96. And then the last thing you do now is you're going to say x1 comma x2 comma s1 comma s2 should be greater than or equal to 0. This, ladies and gentlemen, is your first step, standardizing the problem. Now let's go back to our initial problem. What was our initial problem? That is the next perhaps important thing that we must now do. So last time when we met, we were able to derive our objective function, I believe, which was something like z. Let me try to grab it. So it was 80x1 plus 129x2 subject to 5x1 plus 6x2 is less than or equal to 10,000. So these were assembly hours constraint, and then we also had x1 plus 2x2 is less than or equal to 3,000. These were testing hours constraint, and then the last thing was our x1 here, which was less than or equal to 600, and our x2, which was less than or equal to 1200. So this was our xp, I believe. Was no, this was our basic, I think, our basic computers, yeah, constraint, and then our xp computers constraint. Okay, then the last thing we do is our usual x1 comma x2 is greater than or equal to 0. Now the beauty about the simplex method is, as we will see if we do another question, hopefully we shall, the interest is not really on the two decision variable problems. These are simple, as you will see. Here we only have x1 and x2, but you can be given 3 decision variables. Okay, you can have 30 plus x3. These are the more interesting problems to solve for our simplex problems. But let's go with what we were given in the question. Yeah. Now, as a first thing, or as a first step, which I have already mentioned, is you must make sure that you standardize your problem, or you write it in standard form. So the standard form for your objective function, which is 8x1 plus 129x2, is will come once we have done our constraints. So please make sure that you have the constraints sorted out. The constraints sorted out, and then come back and do your objective function. Now, for our constraints, we have 5x1 plus 6x2, and we have 1, 2, 3, 4. So we have 4 constraints. Just count them in advance. You have 1, you have 2, you have 3, and you have 4. So what do you expect? You expect that your S will range from S1 to SC4. So this, take note, because once we start writing, it will be 5x1 as our first constraint plus 6x2 plus S1 plus 0s2 plus 0s3 plus 0s4 is equal to the number of hours. How many hours? 10,000. So 10,000 hours. The next one was x1 plus 2x2. We don't have an s1 here because this is a second constraint. So it plus 0 s1, and then plus s2 plus 0 s3 plus 0 s4 is equal to 3,000 hours. And then we had an x1 plus, we have no x2, so it will be 0 x2 plus 0 s1 plus 0 s2 plus s3 plus 0 s4 is equal to 600. And then the last one was x, so we had no x1, so it will be 0 x1 plus x2 plus 0 s1 plus 0 s2 plus 0 s3 plus s4 is equal to 1,200. And then here you say x1 plus x, sorry, this should be, I meant to say x1 comma so it be so x1 comma x2 comma s1 comma s2 comma s3 comma s4 should be greater than or equal to 0. Okay, so this is what you do. Now once you have done this, you can now go back to your objective function and basically say plus 0 s1 plus 0 s2 minus, it's minus is actually it should be minus here. So minus 0 s1 minus 0 s2 minus 0 s3 then minus 0 s4. Okay, then standardize it once again. So just say z minus 80x1 minus 129x2 plus 0s1 plus 0s2 plus 0s3 plus 0s4. So we are done here. So this is the standard format or the standard form. All right, okay, so now once we have done that, what is the next thing that must come? So the next thing that must come here is your initial simplex table, right? So we are going to write your initial, you're going to draw your initial simplex table. Now, there are different formats to this table, and they come in different shapes, sizes, and terminologies. But what I found to be the easiest for most students to work with is the table that I'm going to show you. Okay? Now, this table, the first thing that you must have are your basic variables. Okay, your basic variable. So what are your basic variables? So just write basic variable here. Okay, and on top here a bit, even on top we can just write coefficients of, and then here we're going to say you're going to write right hand side RHS and then put ratio here. Okay, put ratio there, and then we're going to close this table just like that. Just draw a nice and smooth line with your rule. I don't have a rule, so don't mind my lines, but for you, make sure that these lines are straight. Okay. Then let's do that. Then let's close this. Yeah, this is too big, but it's too fine. Now on our basic variables, okay, on our basic variables, what I want you to notice here is our basic variables initially must be our S1, our S2, our S3, and our SC4. The slack variables will be our basic variables initially, or on the column. And then the coefficients of here we are looking for the coefficients of x1, x2, s1, s2, s3, and s4. Okay, so we're looking for the coefficients of these values here. So now the last part should be your z function. Okay, your z function. So here we're going to put our z like that. Now we are looking for the coefficients of x1 in the first constraint. So we got the first constraint and look for the coefficients of x1. So x1 we have 5, x2 we have 6, s1 we have 1, s2 we have 0, s3 0, s4 0. So that is what we are going to do throughout in all these things. So I'm going to do them. I'm going to do the first one, second one, and then I'm just going to quickly run through the last one. So for the first constraint, what is the coefficient of x1? Now the coefficient is a value in front of our x1, our x2, our s1, our s2, our s3, our s4. So the coefficient of x1 in the first constraint is 5. So we're going to write 5 here. Okay. What about x2? We have a 6. S1 1. S2 0. S3 0, S4 0. What is the value on the right hand side? The value on the right hand side is 10,000. So we come here and we write our 10,000 like that. We come to our S1. The S1, or sorry, S2, the second constraint. So the value of x1 is 1, so we write 1. The value of x2 is 2, so we write 2. The value of S1 is 0. The coefficient of S1 is 0. The coefficient of S2 is 1. And then we do 0. And here we do 0. Then S3, the third coefficient, we do the same thing. So it will be 1. Then we have 0, 0, 0, S3 1, then 0, and then here we must put our 3000, here we must put our 600, and the last one is S2. So we have the 0 here, we have 1, 0, 0, 0, 1. Okay, yeah, I just want to write them in the straight line with our S1 here. Okay, like that. Now this applies also for our z function. The coefficient of z, these values here, okay, these values here. So we have negative 80, negative 129, and then 0, 0, 0, 0. There. Okay, now this is our initial table. Okay, this is our initial table. Now once we have drawn our initial table, we must now begin solving for our simplex table. Okay, now the first thing we must do is just look at the z function there, or look at the last row of our initial table. Are we there? Now once you have looked at the last row of our initial table, ask yourself a question: which number is the smallest negative? Which number has the smallest negative? Or let's just say, which one is the smallest negative, not which number. Which value is the smallest negative? And we are going to realize that 129 is the smallest negative. Okay? 129 is our what? Smallest negative value. Now, once you have determined that 129 is our smallest negative value, we are going to make the column where the smallest negative value is our key column. Okay, so we are going to circle it so that we don't forget. We're going to circle it from here all the way down. So this is step 1. Okay, so this is number 1, our key column. So key column. Okay, key column. Now once you have found, or once you have determined your key column, step 2 is you must divide your RHS, your right hand side, by the key column. Okay, you must divide your right hand side by your key column. So what does that mean? We want to find the ratio. So to find the ratio here, in fact I have written this here. To find the ratio, we divide our right hand side by our key column. so that if you divide 10,000 or you divide 10,000 by 6, we get 166, 1,666.666, okay, let's say 67. 3,000 divided by 2, we get 1,500. 600 by 0, nothing, so just leave it blank. And then 1,200 by 1 divided by 1, we find, or we get 1,200 still. Now have a closer look at your ratios. Okay, have a closer look at your ratios. Are we done? Good. Now, which one amongst the 3 or the 4 ratios that we have found is the smallest positive ratio? Please take note of the word I've used. It must be the smallest greater than 0 ratio. So it must be a positive ratio. Anything 0 or below, negative or 0, we don't consider them as our key ratios. Our interest here is for a positive, non-negative ratio, the smallest, the closest to 0, but not 0 itself, the closest positive to 0, but not 0. So here we can notice that 1,200 is our smallest. So 1,200 is our smallest. Now we are going to get the corresponding row. And call it our key row. So this will be called our key row. Key row. Yes. Now, take note here that we now have an intersection between our key column and our key row. And the intersection here is 1. Okay? The intersection is 1. Now, this one here, this intersection is called our key element. So take note of all the terminology. They're very important. So the intersection between our key column and our key element is called or is known as our key. Sorry, the intersection between our key row and our key column is called our key element. Okay? So that is our key element, the 1. Now, having found the key element, the next logical step that we must do now is we must ensure that the key element is a 1 in all circumstances and in all places and in all times. Okay? We must ensure that the key element is a 1 in all circumstances and in all times, at all times, as we solve for our simplex table. Now, what I mean is this. Let's say, for example, we had a 3 here. Let's say 3 here. Let's say we had a 3 here instead of a 1. Before you draw another table, the second iteration for a table, you must make sure, or you must ensure that you divide everything here all the way to the last value. Yeah, you must ensure that you divide the values by 3. Okay, divide the values by 3. Are we okay? Are we clear? Is anyone behind? So that is very important. Okay, it is very important because what we want as we solve is to make sure that the key element is a 1. So in our case here, we already have a 1, but I'm saying if it was not a 1, divide everything from 0 all the way to 1200, divide everything by 3. Okay, now we are going to draw our the second iteration of our table here with the same labeling. So we have our basic variable here, variables. So I'm just going to trim this a bit. So basic variable, and then we have our coefficients, and then we have the right hand side and the ratio. Okay, make sure your table is clean and straight. So a table must be clean and straight. Yeah, so just draw the table nice and smooth. Okay, and then okay. Now, once you have done this, what you must do now is, in case you had divided your key row by that number, for example, if it was not a 3, if it was a 3, for example, and then you divided a 3, so it would be 0 over 3, it would be 3 over 3, it would be 0 over 3, it would be 0 over 3, 0 over 3, 1 over 3, 1, 2 over 3. You're going to get your new values and bring them in the second table. Okay, you're going to bring them in the second table. Now, as you bring your values in the second table, this S4 will become redundant. So the terminology we use is the intersection, or the intersection between the key column and the key row. The basic variable, the S4 here, becomes redundant. We don't need it. So it is going to leave our table, and then X2 is going to replace it. So that here now we're going to have our X2. Okay, so it will be X2 here with our new variables. But in our case, it will still be the same variables. Why? Because we have a 1. But if you want, you can still divide it. Say 0 over 1, 1 over 1, 0 over 3, 0 over 1, 0 over 1, 0 over 1, 1 over 1, 1, 2 over 1. Just like that. So we're going to say 0. Then what we have? 1. And then what we have? 0, 0, 0, 1, 1200. So leave it here. Okay, leave it here. Now, once we have done this, what is the next step? The next step now is we want to make the values above. Let's just remove this date which is here. So let's remove that. We remove this. We remove that. So let's cancel some of these things here that are making our table untidy. Okay. All right. Now, what we are saying next is we need to make the values above and below our key element to be 0. What did I say? Repeat after me. I'm just joking. we must make our values above and below the key element to be all zeros. Now, if any value above or below your key element is already a zero, listen carefully. If the values above or below the key element, if you find that there are values above and below the key element which are zeros already, or which is a zero already, what you have to do simply is you're going to lift the entire row and put it in the second table, or the second iteration of a simplex table. So in our case, we have a good example because the value just above our key element is a zero. So what we do is we don't do anything here, because we don't make this a zero because it is already a zero. So what we do instead is we are going to get it the way it is, the entire row. We lift it with our S3 here, we lift it and we bring it into the second table, or the second iteration of our solution. Okay, yeah, so that is what we do. So I'm going to lift the table, I'm looking for the values 1, so we have 1, 0, 0, 0, 1, 0, 600. Don't do anything with the ratios, just leave them blank as they are. Now once you have done this, what is the next step? The next step now is make sure let's label these as row 1, row 2, row 3, row 4, and row 5. It will make your life easy, as you will notice just now. Now once we have done that, what is the next step? Okay, now what you want to do, as I have mentioned already, is we need to make this row, this 2 here, to be a 0 with the help of our key element, this one which is here. Are we together? What I'm saying is we need to make this 2, the 2 which is in row 2, to be a 0 with the help of this one which is in row 4. So what we do is we are going to say we need to make row 2 0 with the help of row 4. Okay, with the help of row 4, this row 4 here. So what we do is this: we are simply going to say the first step, just make sure you say R row 2 minus row 4, row 2 minus row 4. Now it is row 2 we are trying to make it to turn into a 0 with the help of our row 1 here. So the easiest thing you can use to think about this is just get this 2 and bring it in front of our row 4. Okay, grab the 2, bring it in front of our row 4. Okay, are we together so far? Are you lost? Yes, you are. I know you are lost. So just rewind the video, watch it again, and try to understand. So what I'm saying is we need to make all the values above and below our key column, our key element, sorry, to be zeros. Now for the first one, this value, the 2, we need to make sure that 2 becomes a 0. So how do we make 2 become a 0 here? The only way we can make 2 become a 0 is by subtracting 2 minus 2. Right? Now, you just can't do 2 minus 2 here. Why? Because you're going to get into problems when you come to these other elements. So instead, what you do is, you know that 2 minus 2 is 2 minus 2 is 0. But this 2 cannot stand on its own. It needs the help of the queen mother. And the queen mother in this column is a 1 here. And where is this one? This one stands in row 4. So just put row 4 in front here. Okay, that is what we are saying. Put row 4 in front. And we know that 2 is in row 2. So we can make this a formula. Just do row 2. That is all we are saying. Okay. So this is how we are going to make it row 2. That key, that element to become a 0. Now, what about the row 1? How are we going to make row 1 to become a 0? This row or this element here. How can we make it a 0? The only way it is subtracting 6 minus 6. You see now? 6 minus 6. But it cannot stand. This 6 cannot stand on its own. We need to add an R4 here. It means we are making the 6 a 0 with the help of a key element. So then just put R1 here. So this is simple, as you have seen. So it will be R1 minus 6 R4. Okay, so this is for 1. Now we can start solving our problem. Yeah, let's start solving our problem, which we have already done. So this is a 2, so we're going to use the first one here. So it will be 2, where there's R1, R2, sorry, R2, yes, minus 2, open bracket. What is R4? R4 is simply a 1, this one here. So just come here, put a 1, then say it is equal to 2 minus 2 times 1 is 0. So we're going to put a 0. So we have S1 and the S2 here. So we're going to put a 0 where there's S2. Okay? Yeah, here where there's S2. S2 is here. So we are putting a 0. How do we make this 6 to become a 0? We have said it's R1 minus 6 R4. So what is R1? Our R1 is 6 minus 6, open bracket. What is our R4? Our R4 is 1, is equal to 0. So we put our 0 here. Kwaman. Okay, we are done with the first part. Now, once you have done that, we come to our second part now. We need to fill in the remaining blank spaces. Now, the way we fill them in, okay, the way we fill them in is the same as what we do with the key column. Take note of that. So here also, what we are going to do is I'll try to be writing it here, and then I will in fact I'll be writing them here. Let me just remove some things down here. Yeah, so that people can be seeing what we are doing. So the last thing, sorry, I think we forgot to do the this one here. So how do we make negative 129 to become positive? It is negative 129 plus 129. This is how we are going to make negative 129 to become a positive, a 0. Okay, so therefore the formula for this one will be R4, is it R4 or R5? Yes, R5 plus 129 R4. This is how we make it a 0. So what is 120? What is R5? We have negative 125. plus 120, 129, not 125, 129 plus 129, open bracket, 1, you close it, you have a 0 here. So even here we are going to put a 0 like that. We're making progress. Now we are done with the key column. Now we come to our other columns. Okay, now why are we doing all this, you may ask. The reason is very simple. The reason we are going through all this trouble is because at the end of the day, for this question, if we do 2 iterations, because we only have x1 and x2, which are our variables that we actually need to make a decision. Once we do 2 iterations for this one, or 3 iterations, we must make sure that we have no negative values in our objective function. All the values must be positive. We don't need any we don't want to see any negative. So at the end of the day, if it so happens that you see a negative value in the objective column or objective row, yeah, it is a row, you must make sure that you continue to iterate until it is no longer negative. There are some problems, however, just like the graphical method, which are unbounded or infinite. So you can iterate 16 times or 5 times, you still have a negative value. So for such cases, there may be no solution, yeah, to some values or for the entire question. Okay, now we have made this a negative, a 0. Now what do we do? What we do now is we need to solve for the remaining parts of our question, of our tables rather, the blank parts here. Now how do we go about solving them? It is very simple. Okay, it is very, very simple. And I'm going to continue solving that in the next video.